Hello, everyone. So today we're going to be talking about modality matching matters, calibrating language distances for cross-lingual transfer in URIEL Plus. So here with me is York. So I'm Aditya, and we're both undergrads from the University of Toronto. And I thought it'd be nice since we're both here, may as well just co-present, right? Like do a little bit of stuff for both of us, right? But this really was a kind of like collaborative effort from a bunch of different universities. So we are very, very proud and very, very thankful for everyone who helped out on this project. Okay, so this is the kind of setting that I want you to keep in the back of your heads throughout this presentation, right? Suppose that you want to do some kind of task in Haitian Creole. Now, obviously, there's not a lot of information about Haitian Creole on the internet, right? It's pretty low resource language. What we do have a lot of information on is high resource languages, right? So two potential kind of examples of them are French and Russian. So one kind of thing they might consider doing is training a model on French or Russian and do some kind of transfer learning, right? So cross-lingual transfer is the term for this. Now, naturally, you would kind of immediately think that French is probably the language you want to train on and maybe not Russian, right? French is probably a little bit closer to Haitian Creole, right? But what did you actually think about when you made this decision? What you were thinking about is how distant French or Russian are to Haitian Creole, right? So implicitly, what you're doing is that you are kind of thinking about how distant they are, and you need a measure of kind of language distances, right? The more general problem here is that we want to do some kind of task in some low resource language X, and we have maybe some multiple choices of, high resource languages. How do we choose the optimal high resource language as a source language to do some kind of task in some kind of target language? Okay. In other words, to do this, we need a good measure of language distances. Okay. So here's the kind of way that we try to approach this. So this is actually one of my papers that I published last year. We talk about URIEL Plus, right? And URIEL Plus is kind of a linguistic knowledge base that computes or that allows you to compute distances for three different types of modalities for languages, right? So geographic, so this is where languages are spoken around the world. Genetic, this is basically kind of describing the shared ancestry of languages, on a family tree. For instance, like you can kind of imagine English being related to, say, German through a family tree kind of relationship, right? So on and so forth. And typological, right? And so this is like differences, structure, grammar, phonology, morphology, even of different types of languages. And we kind of encode this kind of information for each of the 8K languages within URIEL Plus. It's actually extended now in a recent paper that we're also publishing. Yes, it is 23K. But yes, you're basically representing each of these languages as vectors for each of these modalities, right? And you can compute distances because you have represented these languages as vectors, right? And actually, URIEL Plus and its predecessor, URIEL, are pretty widely used in downstream NLP tasks. I just want to point out some of the papers that are kind of using this. For cross-lingual transfer, it's used, it's actually a paper at EACL who's kind of like using this Aku and Pullman. It's used in dependency parsing, it's used in machine translation, it's used in speech recognition, and it's also used in LM regularization. So yeah, big shout out to the papers at EACL who are using this already. So, people do find this kind of useful for downstream like NLP tasks, right? You often need a kind of like language distance measure. That kind of gives you a general kind of overview, and I'll let York kind of take over on talking about what are the actual issues with URIEL.
Well, thank you, Aditya, for talking about the utility of URIEL Plus. Now, you're going to have to forgive me a little bit because I need to talk about some of the limitations of your paper. And the key limitation to URIEL Plus is in how they compute these distances. So you'll notice that URIEL Plus treats all three modalities in essentially the same way. They represent them with high-dimensional Euclidean vectors and then calculate language distance via angular distance between those vectors. So for the geographic modality, the underlying assumption in those vectors is that languages are spoken at a single point. So you notice that English is represented by London, French is represented by Paris, etc. And so for these European languages, the distance between them is extraordinarily small. And that obviously tells you that it is encoding some kind of Western-centric bias. And then for the genetic modality, URIEL Plus's genetic vectors and contain over 3,000 features, each of them being a binary encoding of whether a language is in a certain language family. And so, and a really big limitation of this Euclidean approach is that it's the assumption that all language family splits have the same impact. So for example, Hindi and German are, they split at the Indo-European language family, and German and English split at the West Germanic language family. And in URIEL Plus, this is assumed to have equal weight. And But then in our case, right, we see that these distances are unusually high, and that is encoding um, some kind of issue with the geometry that is being used. For the typological modality, the typological vectors in URIEL+ have 800 features, and a lot of them tend to be correlated in reality. So, for example, the syntactic feature of word order is operationalized in URIEL+ as multiple features, one for SVO, one for SOV, one for OSV, etc. And this gives us a lot of noise in our distances. Now, my paper at EMNLP demonstrates that the high dimensionality of these representations limit their effectiveness. In this paper, now jointly, we claim that language representations should match the structure of the modality that it is trying to represent. And this is how we do it. For each modality, we construct a new, unique representation that is modality matched. And for each of these representations, we built a unique distance function that gives us modality matched distances. And this table summarizes how we do it. And I'll talk about them in order. For the geographic distribution, we want to account for the fact that languages are diverse. They're spoken in tons of different places around the world, even for English, especially for English, actually. So we move from treating languages as a single point to modeling the distribution of languages across the entire world, where we measure for each language the proportion of speakers in each country. And this allows us to capture, for example, the fact that in the United States, there are tons of speakers of English and Spanish, and this has been historically a place of language contact between the two languages. And as we can see on the figure here, the distances we get are a lot more realistic. For the genetic embedding, we study a different way of encoding or embedding glottolog. So glottolog is a catalog of the world's languages and the family tree that unifies all of them. And in URIEL+, while this is embedded as a one-hot encoding of glottolog, we instead embed this in hyperbolic space. Now, hyperbolic space is a natural choice for us because it is a geometry that has been demonstrated to be better suited for tree structures rather than a Euclidean geometry. And this figure here demonstrates kind of what that might look like for a 2D Poincare disk. And how we operationalize this is with a contrastive loss function that pulls together related languages and pushes apart unrelated languages. And we verify that this actually does give us a representation that preserves hierarchy by measuring reconstruction loss. And we see that with a hyperboloid method, with a hyperboloid model with 10 dimensions, we get a reconstruction loss that is substantially higher than the Euclidean model. And then finally, for the typological modality, we, instead of the URIEL+ approach, which is represents languages with high dimensional vectors that have groups of correlated features, we instead group those groups of correlated features together into latent binary variables, which we call an island. Now, an island contains groups or multiple typological features, where we kind of guess that there should be some underlying factor that governs that group of features. And sorry. And we do that with a latent tree modeling method where we use a greedy algorithm and based in information criterion to determine the best way to group up our features. And the intra island correlation is 0.6, which is really surprisingly high given the amount of noise that is in URIEL+, and this demonstrates that we are actually producing some meaningful clusters here. Now we finally move on to talking about the performance impact of our representations on URIEL+ or on some kind of downstream measure. And for this, we use a task of transfer language selection. And this is a task that is widely used with respect to language distances. And it is founded on the idea that a lot of the time in multilingual NLP, we want to perform a task in some low resource language where we don't have a lot of data, but maybe we do have some kind of some set of models that are trained in a different but similar high resource language. So our task setup is this: we are given an unseen language, 2, a set of models trained in a different but high resource language, and 3, the language distances between the unseen languages and the set of model languages that are used to train the models. We train a ranking model, which is called LangRank, from 2019 to predict the model that we expect to perform the best for that unseen language. And we measure the performance of LangRank with a metric called performance loss, which is the relative gap in performance between the model that LangRank chooses to be the best and the model that is actually the best, so the optimal language. And we measure the impact of our new representations on this performance with an ablation study where we swap out URIEL Plus's distances with ours when we train LangRank, and then we perform a regression analysis that tells us what the change in performance is when we use our new distances. And we repeat this for every downstream NLP task that we study. So we study 9 downstream NLP tasks, and this is, to our knowledge, the biggest evaluation on cross-lingual transfer, zero-shot cross-lingual transfer. And that includes dependency parsing, entity linking, machine translation, part-speech tagging, and 2 tasks of text classification and natural language inference. And we find, so we report the baseline performance loss when using URIEL Plus, and the colored bars, although they're not very clear, show the change in performance loss, or the expected change in performance loss when we swap out the URIEL Plus representations with ours. And we find that for every task, there is always some combination of that swapping out we can do to reduce performance loss, which is what we want. And in fact, some of these impacts some of these representations impacts are really profound. So for example, if you look at the bottom, the first row, but the bottom row of that, the hyperbolic representation reduces empty performance loss by 4.5, which is actually a decrease of 36%. Or if you look at the second row with the islands row, it reduces XNLI performance loss by 39%. And these are really, really substantial results when it comes to reducing performance loss for cross-lingual transfer. So takeaways of our paper. Our takeaways are twofold. The first is that we argue that when representing languages, we have to match our representations to the modality that we are trying to match. And indeed, our modality-matched representations have been shown to consistently outperform URIEL Plus in cross-lingual transfer. However, we notice that between modalities, the utility of that modality is dependent on the task that we are evaluating on. And so we argue that there really is no one-size-fits-all solution for when it comes to cross-lingual transfer, and that we can uniformly just simply apply all language distances at once to modeling cross-lingual transfer. And that is the end of our presentation. Here's our paper, here's our code, and our emails. Thank you very much.